Hello, and welcome to Lecture 6 of DSci 522, Workflows for Data Science. In this lecture, we're going to start to get to know a tool called Docker. This is going to allow us to create shippable and shareable computation environments. By the end of this lecture, you should be able to explain the difference between running software or scripts using something like a virtual machine versus a container approach like Docker. And you should be able to use Docker to run some software on your laptop. So let's talk now about documenting and loading dependencies. At this point in the course, in your group projects, you should be very familiar with this. But let's just go through this thought experiment to just bring it to the forefront of our mind. So you've made some beautiful data analysis pipeline project using R and or Python, and it runs on your machine. But how easily can you or someone else get it working on theirs? And the answer usually is it depends. What does it depend on? Well, it depends on whether your README and your scripts make it blatantly obvious what programs and packages need to be run to do your data analysis pipeline or project. If these things are not blatantly obvious, what happens? You've probably experienced some of this maybe in your group labs or in some of your, in this group project where you'll start to run the code and then it will break. It'll break because you're missing a package. You'll install that package, you'll run it again, and it'll break again because you're missing another package. That's why we need to make it really blatantly obvious at the top of the script or in our README, what are all the things that I need to install to run the project. That's one way of doing this, and it's a good way. But when we do this, we also often forget sometimes to document the version numbers of the programs and packages that we use. Because just having those things will maybe let our code run, but maybe it won't give us the same answer that somebody else got with that package on a different computer because they have a different version. Now, there's a hint in the lecture notes here. Remember the changes to the random number generation in R from last year. Well, last year, the R programming language changed how it generates random numbers. They use a different algorithm. So the same seed 1, 2, 3, 4 in R before from more than a year ago will give you a different random number than it would give you this year. That is kind of crazy, but it happened. So what that means is that even though you've done a lot of things in your script to make them reproducible, if you run it on a different version of R, you'll get a different number. So when we're documenting and loading our dependencies, not only is it really important to make them upfront in our READMEs and scripts, we also want to talk about what versions we're using. Now this is a lot of overhead, and it can get kind of tiresome and maybe not seem fun or important, but it is really important for making accurate and reproducible code. It's not the only thing that makes things accurate, but it's helpful. So are there some tools that can help with this? So one tool that you've already encountered in the MDS program is Conda. And that's a way to do a small virtual environment that you can share along with your code. And you've learned how to use that with Python. You can also use it with R, but there are some more R-friendly tools like RM that are often used in R in place of Conda. And you can use Conda for things outside of Python and R. However, there are limitations to all the things that Conda can manage with making your environment shippable and shareable. So if there are things like legacy code and that's in some other language, some kind of like operating system libraries and such that your code depends on, then you might want to use a tool that's more powerful than Conda for shipping and sharing your environment. And one such tool is called Docker. So Docker is a tool that has multiple, I guess, like adjectives around it. So there's images and containers, and we'll talk about what these each mean. But basically, you can think of Docker as a piece of software in a complete file system that contains everything needed for your code to run. So it's going to have system packages, operating system packages. It's going to have the programming language and the programming language packages. And depending on how you create your container and how you version your container, this can somewhat guarantee that your software will always run the same regardless of which laptop it's running on, because it's running really in the same environment across multiple laptops. So let's talk a little bit about, so Docker is a piece of software, for containers or containerization. And let's talk a little bit now about how that differs from a virtual machine. So maybe I should step back and just say, like, what is a virtual machine? Well, on top of your laptop, you can install a virtual machine software, and that could run a whole other operating system on your laptop. So for example, I typically use a Mac operating system, but I have in the past wanted to test things on Windows before I owned a Windows laptop. So I would install a Windows virtual machine on my Mac laptop so that I would be able to work in a Windows environment and run things in the way that Windows runs things. And this is kind of what it looks like conceptually on the right-hand side, where this is like the infrastructure of my laptop. My laptop has a hypervisor, and then there's a guest operating system for the Windows, and then there's some apps that are installed on there, okay? This is a very big box. It's very memory intensive and quite large. Containers, on the other hand, are more shippable and shareable and lighter weight. So we have our laptop infrastructure, and then we have your host operating system. So this would be like my Mac operating system. And then on top of that, I've got Docker installed. And then inside of one of these squares here represents like the container software. And that container software would have things like operating system packages for Linux, because I'm mostly running Linux containers, but it doesn't have to have the Linux operating system. Docker does the job between converting or communicating those Linux system packages with kind of like my host operating system. And inside of here, it would also have the programming languages and the packages that I need for running my analysis. So I get a smaller box that is more lightweight and more shippable and shareable than a whole virtual machine that has to have the entire other guest operating system, okay? So the key take home here is that Docker creates a more defined environment that something like Conda would do, it's less porous than Conda, okay? So it's more closed off, but it's more lightweight than an operating system, and an operating system is super closed off and hard to actually communicate between the memory shares of these two things. So that you can use this to share an environment easily with other people on their laptops, and you can, at the time that you want, make it as porous as you need so that it can access the files on your laptop. Now, this is still pretty abstract at this point, and that's okay. We're going to work through some examples today so it becomes a bit more concrete. So let's do a motivating example. So we have been using Makefiles to automate and create our data analysis pipeline this week. And one thing that could be really nice for this is to create a dependency graph for these data analysis projects, where we have bubbles that represent the different files, so our data files, our intermediate data files, our scripts, and our source documents, and then arrows that show how they all connect in the dependency tree that we've created in our Makefiles. So this Makefile to Graph program can create this for us from our Makefiles. A real life problem is that Makefile to Graph is a pain to install, not just on Windows, especially on Windows, but also on my Mac. So I don't like installing it every time I get a new computer, and I use it, semi-frequently. So what I prefer to do is use a Docker container that I've previously built to run this software on my laptop. Every time I get a new laptop, I install Docker, and then I can just use these containers that I've previously installed things in and use them to run the software and connect those containers to my laptop, okay? So let's do it. So step 0 for this is install Docker. You do this once every time you set up your laptop. And you should have already done this when you first came to the program many months ago when you went through the MDS installation guide. If you don't see Docker in your when you go to follow along with this lecture, please do refer back to the MDS installation guide to install this. The next step that we need to do is to launch the Docker app if we're using Mac or Windows. You don't have to do this in Linux because Docker is a native Linux application, but on Mac and Windows you do. So to check if it loaded at launch, which it often does on your Mac, you can go up to the menu bar up here, and if you see this little whale and this dot is green, your Docker desktop is running. On a Windows machine, you would typically see this down in your right-hand corner of your laptop, where you have all your other kind of like little notifications about whether your Wi-Fi is connected and those sorts of things, okay? If you don't see these things running, then you'll want to search through Launchpad, Finder on Windows, or the Start menu in the search bar on Windows to find Docker and click on the whale icon to launch the program. Then the next thing we need to do is to get the container from Docker Hub. So what is Docker Hub? Well, Docker Hub is very similar to, you can think of it as analogous to GitHub. So, but it doesn't store code, it stores and shares Docker containers. So it's like, yeah, it's like it's a container repository, like GitHub is a code repository. So how we will go do this is that we open some sort of terminal or git bash if you're on Windows, and then you'll run docker pull ttimbers/makefile to graph. And this docker pull is very much like a git pull or a git clone. There's not really a docker clone that you'll be using. You just start away with docker pull. And that will go to the remote, which is Docker Hub, and take that image and bring it down to your laptop. And then after that, you can type Docker images. And you can take a look, and if you have something that kind of looks like this, and I'll demonstrate it as well, inside of your terminal after you run Docker images, then it will indicate that you have been able to successfully pull that image. Now, one thing that I would like to stress is that this one's not too big, but it's still fairly big. I said they're lightweight, and that they're lightweight compared to virtual machines. They're not lightweight compared to kind of YAML files, okay? So this makefile to graph is 469 megabytes. So make sure you're not like hotspotting on your phone, or if you have like not great Wi-Fi, you might want to do this like ahead of time before you plan to actually use the image. Okay, so I have my terminal open, and now I want to pull the Docker image. So I'm going to type docker pull ttimbers and then make file to graph. Let's see what happens when I run this. So it is going to start downloading this image, and it has to download it, it has to extract it, and then it has to happen for all of these rows, and I'll explain what these rows are in a minute, for it to successfully end up on your laptop. So when we start learning how to write our own Docker files to make Docker images next lecture, you'll learn that these things are created in layers, okay? And that's to help make them more lightweight, and so that you're never really duplicating. If you have two related images, they don't take up two independent equally amounts of space on your laptop, that the shared stuff will just basically be one shared memory store, and then you'll have layers where they diverge at the end. So each of these rows refers to a layer in the Docker image, okay? And we get a unique identifier for each image, so that's what this SHA is here. And then we get a status output that we have this newer image downloaded, and this is the image name. And then we have a colon, and on the right-hand side is the image tag. And we'll learn more about image tags next lecture. So this looks like things worked well. Let's run that Docker images command to list all of the Docker images on our laptop. So I am going to stretch out my terminal so that this is a little bit easier to read. And what we get when we type Docker images, and I can maybe make this a bit bigger, is we get a table where we get the repositories. So these are the Docker images, and on Docker Hub, each image has its own repository, kind of like each project on GitHub is its own repository. This is the tag that we're going to learn about in later courses. This is the short part of that unique SHA for each image, and then when the image was created and how big they are. So we can see that the one that we just pulled is here, that I created this thing 4 years ago, and that it is 496 megabytes, or 469 megabytes. So what is the next thing that we'd like to do? Let's, maybe before we go into running this container, maybe I can take you to Docker Hub and show you where did this thing come from and what a Docker Hub repository can look like. So here I am on Docker Hub. I have created an account and I'm logged in. And I have created several repositories on Docker Hub, and so you can see them listed here. When you run into Docker Hub, or when you log into Docker Hub, you might not have any repositories yet, but you can still explore other people's repositories and use them. So you could search for Timbers up here and look for my repositories that way. And this one is actually the one that we're interested in. Timbers make file to graph. So let's go here. So this is the repository on Docker Hub where this image lives, and this is where we pulled it from. There's a description here, kind of like the README, and then there's some commands on how to get going. And if you have linked it to a GitHub repository where the instructions for and the code for how this thing was created might live, you can link this as well. So this is the GitHub repository where I have the code file that created this image. Let's clear the screen. Now let's run the container. So to run a container, we type docker run, okay? And then we're going to say that at first, at least, we're going to run this thing interactively so we can get to see what a Docker container looks like and get more familiar with it. So there's a command to run it interactively, which is -it. And then the next thing we have to say is which Docker image we'd like to run. You probably have two on your laptop, the hello world and make file to graph, but I had several. And so I have to say Docker which one. Timbers make file to graph. And I'm going to hit enter now. And what do we notice? Well, we notice if this works that our prompt changed. So we had a $sign and maybe something about our path or our user when we were in our computer's terminal. But now we've changed environments. We can see that we see a hash symbol at the end of this prompt, and that hash symbol indicates to us that we are likely in a Docker container. And this SHA is linked to the container identifier. And we'll talk about the differences between images and containers in a minute, but just bear with me while we get to know what a Docker container is. Okay, so this Docker container, is kind of like being inside of a terminal on a Linux computer that's living on our laptop. You can kind of think about it this way. So I can use all the commands that I could use in a Linux terminal here. So I can type ls and I can take a look around. I can say print working directory. Where am I on this computer? So I happen to be in the root of this Linux, this mini little Linux computer, which is really a Docker container. And I can see folders like a home folder and a bin folder and an opt folder where things might be stored and a user folder. And I can make new folders. So I could say make dir and say I'm going to have a project named Pony. So I could make a Pony directory. And then I can type ls, and then I can see that I have created said Pony directory. I can navigate into the Pony directory, just like I would in any other terminal, and I could create a file there. I could say touch test.txt. Okay, so this is very much like a Linux terminal, and you see that that file's there. Now, the thing to know is that we haven't done anything special to link this mini Linux computer or this Docker container that's running Linux to our laptop. So when I type ls here in Pony, or if I type ls in root, these are not the folders and files on my computer's root, okay? They're the root of the container. I haven't done anything to link this container, make it porous to link this container to my computer's file system. It's completely closed off right now. We will do that, and that will be useful. We're going to work our ways towards that. The other thing to note is that if I exit this container and then I destroy the container and I launch a new container from ttimbers make file to graph, this file isn't going to exist anymore, and this pony directory is not going to exist anymore. So the way you should think about running containers is that everything inside of this container's file system is ephemeral, and really what you want to use a container to do is give you an environment and then make it porous so that it can access the files on your computer's file system and work with them there, okay? And when you close that container down, because those files were edited and saved on your laptop, they will persist, and those changes will persist. So anyways, let's move along. How do we get out of this container and get back to our Linux terminal? We type exit, and we can see that our prompt changes again to here. So one thing to know is that if we launch a container like this, the container is still hanging around in our computer's memory. And every time you run this, you make a new container. So over time, as you run this image many times, you're going to have a whole bunch of these containers hanging around, and they're going to eat up memory on your computer's file system. So you need to manage and take care of that. So we can view any existing containers on our laptop using a command called docker ps-a. And we can take a look, and I can see that there are two. I'm going to zoom out here just so that it's a little bit easier to see. Yeah. Actually, 3 containers hanging around on my laptop, and I should shut these down. So how can we do this? Well, there's a command called docker remove and then the container ID. So here we have this column of container IDs. Let's get at least rid of the one that we were working with. So I can say docker rm for remove, and then I will copy and paste in the container ID. And then when I type docker ps-a, oops, that's -1, docker ps-a, that container is now gone. So there's no ttimbers make file to graph container hanging around. Now, it's a bit, I guess, annoying that you would have to do this, that you launch your container and then you have to do something, you have to type exit to get it out, and then you have to like docker ps-a to get the container ID and then docker remove to shut it down. So there is an easier way. When we launch our Docker containers, I'm going to clear again and resize this just to make things a little bit more viewable. We can say docker run -it, and then we can add this flag called --rm. And what this --rm flag does when we run our container is it says that when we exit the container, I don't want to leave it hanging around. I want to delete it. So this is what I recommend that you do every time you use docker run. Okay? And then you prevent yourself from having all of these containers pile up in your computer's memory system. So let's do this. So we'll do, the last thing we need to add is the name of the image we'd like to make our container from. So make file to graph. And we're back in the container. And this time when we exit and type docker ps-a, we, again, I guess I'll resize. Apologies. We don't see that container. We just see those other 2 that I haven't shut down. Okay, so do add this --rm flag when you are running your containers so that when you type exit or quit them through another method I'll show you for certain containers, that they don't hang around and clog up your computer's memory. Now I've been using 2 terms, Docker container and Docker image. What's the difference between these 2, and why am I using 2 terms? Are there actually 2 different things, or am I just mixing words up? So there are actually 2 different things, and they have meaning, and I'm trying to be intentional in when I use them, so I'm using them correctly. But let's formally define them now and give an analogy. So the image is what the containers are made from, okay? So the image is, you can think of it like a program. So a good analogy is the program Chrome. So you have, the Chrome browser installed once on your laptop. So similarly, we have one copy of the Docker image installed on our laptop or pulled onto our laptop. And then like Chrome, when you click on that Chrome browser icon from the program that you downloaded, you get an instance, right? You get a window, you get an instance of that Chrome program. And when you close it, it goes away. But the Chrome program still exists on your laptop. The container is like this instance of a Chrome window. So when you say Docker run some image, from that image, it creates a container instance of that image. And then when you exit it and destroy that image, then it's gone. You still have that image on your computer. Okay? So you can think of a Docker image like a program on your computer. And a Docker container is like an instance that you're running of that program. Here's another schematic from a blog post by Arnaud Mazin. So this is our computer in the bigger gray thing. And you have Docker running, and Docker is going to manage both images and containers. Images, we got ours from Docker Hub, so we pulled to get it here. We're going to learn next lecture that you could also use a file, like specifically is called a Docker file, and use the Docker software to build an image. And then once an image is built, then we can use Docker run to get an instance of the container. The container is actually the thing that's going to have the compute environment and going to allow you to run your software, your R program, your Python program, for example. And this is the thing that you should think of as like an ephemeral instance that you use while it exists, and then when you're done with it, you just shut it down. But the image always stays around on your computer, or at least on the Docker registry, or some record of how it may be built again in a Docker file. So the next thing we're going to learn to do is to use a command in Docker called volumes, or we refer to it in a Docker command as -v, to mount files or folders from our laptop to the container. Because remember, we want these containers to be ephemeral. So when we are done using them and we exit them, they just disappear. So the reason what we're using containers again is to not store our files or folders inside the container, but to access the software that's inside the containers, because it's really easy to ship and share these containers with other people. And we use the software inside the containers to modify and manipulate and create files on our laptops. And then to share those files, we would actually use something like GitHub, as we've already been doing, to share those sorts of files, okay? So it's two different types of sharing going on here. Now I'm ready to run my container and connect the container to a volume on my laptop so I can access some files. So remember to run it. We start with Docker run. Then we use -it to say we'd like to run it interactively. And then we say --rm. And that's to make sure that the container is ephemeral and it's automatically destroyed when we exit it. And then we want to add the new one, -v. And on the left-hand side, we have to say an absolute path on our laptop of where the files or folders we'd like to share with the container are located. So for me, that's in users, Tiffany Timbers, desktop, and then in data analysis pipeline, EG. And then I'm going to hit colon, and that colon is saying, okay, that's done what's on my laptop. Now I'm going to specify where I'd like this to show up in the container. So I want to start from, these have to be absolute paths on both sides. So I'm going to start with the root, which is the slash here, and then home, and slash. We're going to make a new directory in home, and I'm just going to copy and paste data analysis EG so it has the same name. And I'm going to hit enter. And I forgot something. I forgot the name of the container. So let's add that name of the container. Timbers, make file to graph. And we're inside the container. We can tell by the hash here. So let's look around now inside the container, and we see we have this home directory. So let's go into home, cd home. And now let's take a look inside home. We have this folder now called Data Analysis Pipeline EG 2.0 that wasn't there the first time we ran the container. Let's go inside of there and take a look at what's inside of there. So we have all of the things that we were working on last lecture. So we have all of this, we have the src directory, we have the doc directory and the data directory, we have our make file. So we can access everything on the laptop these things don't exist in the container. And to prove it to you, I will exit the container, and I will re-enter the container with a command that we used previously by basically removing this -v with the file mounting, and we'll look at home, and we will not be able to see those files. So if I go ls home, there's nothing in the home directory, okay? So it's this -v, the name or the path, the absolute path on your laptop of the files or folders you'd like to connect, colon to say, that's the end of that on my local, what's coming next for the container, and then the absolute path on the container of where you'd like things to go, and then what you'd like that folder to be called. Okay? So one thing that is a bit annoying is to have to type out this entire path. One nice trick, which I'll show you now, is that, and I'll clear just to make it easier, is we can do docker run -it -rm, and then when we do -v, instead of typing out the path, you can do $pwd. And then you can say on this side where you'd like things to go. So we'll go home and just, I'll call it DA for short, and then the name of the container, ttimbers, make file to graph. We'll end up in the container, and then we say ls home. We can see DA, and if we say ls home DA, we can see that I mapped it to the current directory that I was in, which was my home directory. So that wasn't exactly what I wanted to do. So when you do this $pwd, it's whatever folder you're currently in. So to have that actually work correctly, I would have to navigate to the data analysis folder, right? PWD. These are the folders and files that I would like to share from this path, and those are the files and folders that I'd like to share with the container. Now if I run that docker run command, when I type ls home DA, I see the files that I'd actually like to share with the container for creating this make file to graph dependency diagram, which we're going to do in the next lecture video.